Hello, my name is Tracy and Bruce-tagoe, and I'm presenting on the predicting trends in foodborne diseases using the CDC foodborne disease outbreaks 1998 to 2015 data. This presentation is going to cover the background, methods used, results and discussion, conclusion, and some recommendations, and then references. To get started, it is estimated by WHO that every year about 600 million people get sick from foodborne disease outbreaks, especially in developing countries. Unfortunately, as huge as this number looks or sounds, it is way higher in real life because a lot of the diseases that are obtained from foodborne pathogens, or a lot of the foodborne disease outbreaks are not reported. They are treated over the counter, and so they do not go into the books. So this is just an estimate, which is like a smaller estimate of what the real life thing is. And out of this estimated 600 million people, about 420,000 of them are reported dead every year, and 30% of this huge number are children, which is very sad. 110 billion US dollars is lost yearly in productivity and medical expenses because, of course, if we are losing this number of people, some of them are workers and all of that, then we are losing in productivity, and we are spending a lot of money in medical expenses trying to treat the outcome of these foodborne disease outbreaks. Now, over the years, scientific research has focused more on developing and modifying pathogen detection methods, which is because most of these foodborne disease outbreaks are caused by foodborne pathogens. Foodborne pathogens are a group of microorganisms that cause diseases. They include bacteria, virus, and parasites that are found in food, and they contaminate the food. That when you take the food in, they cause diseases, and these diseases lead to one case leads to many, which becomes a full-blown outbreak. But in the bid to fix this, or to reduce how much loss goes into foodborne disease outbreaks, scientists concentrate more on the detection methods, which is good. And so far, we have gotten a lot of methods to detect these foodborne pathogens, and it has reduced significantly the number of diseases that are recorded yearly. But we cannot overlook the importance of analysis of data. It is very necessary to study the trends in the data obtained from past outbreaks. This will help the relevant authorities make good decisions as to how they can prevent further outbreaks, future outbreaks, or how to deal with even current or past outbreaks. Now, this work seeks to find the trend in the data. That is the data that is obtained from the CDC website covering outbreak information from 1998 to 2015. So this work is looking to find the trends in it, whether there is any relationship between the variables in this data, because there exists a school of thought that thinks that because people are more interested in quick meals these days and are less interested in the traditional home cooked meals, and most foods are eaten from outside, that is why there is still many cases of foodborne diseases currently. Even though we are in times where sophisticated methods have been created for pathogen detection, we still have considerably very much cases, or a lot of cases that are not supposed to be so, and people associate this with the fact that more people are interested in eating quick meals. Looking at the data set that we are working with, we are working with the CDC's data, which has 19,119 rows and 12 columns. The data generally contains specific information concerning foodborne diseases reported between 1998 and 2015 in the US. So this data covers the years between 1998 and 2015, the months when the report was made, the states in which the report was made, or the states in which the illness occurred, the location in which the illness was reported, so mostly the location where the food was eaten or obtained, the type of food that caused the illness, sometimes the ingredients that was used to prepare the food are also listed, not often but sometimes, and the species, if known, that caused the diseases. Now, some of these species include Salmonella typhi, Listeria monocytogenes, norovirus, Staphylococcus aureus, Escherichia coli. All these are types of pathogens that cause serious foodborne diseases. Sometimes the serotype or genotype of these bacteria or viruses are also known. Most importantly, the data also include the number of illnesses that are recorded, the number of hospitalizations, and the number of fatalities that are caused. That is the overlook of our data that we are working with. Moving on to the methods that we would use in this data analysis work, we would start by prepping our data. Now, preparing the data for the analysis includes or starts with loading the data set into Pandas data frame. So originally the data is a .csv file, or which can be I exported my .csv into an Excel file, so it became a .xls file, which I loaded into the Pandas data frame. And then the next step after loading the data is for it to undergo cleaning. So the essence of cleaning is to take care of missing data, because a lot of the data that are posted on websites have a lot of missing data. If we look at the data I showed earlier, the table I showed earlier, you would realize that some parts of the data had NaN. Those are missing data. Exactly. But for my case, I decided not to clean the data, because when I attempted to clean the data, there was a significant loss of data. What I mean was, when I ran the .drop_na function on my data set, I realized that I was left with only about 590 rows out of the 19,119 rows that originally came with the data, which is not even up to 10% of the total original data, and hence cannot represent the population very well. So I decided against cleaning the data, since it was going to cause me to lose much of my data, like majority of the data. So from loading it, I went ahead to do some exploratory data analysis. Mostly what I did was to visualize part of the data to see what is really going on in the data, and most of those visual plots will be seen in the next few slides. From there, I had to choose two methods that I was going to use mainly for the analysis of this work, and I chose regression and clustering, specifically linear regression and k-means clustering. So this is the very first plot that I made. This plot is technically a bar plot, which is showing the number of illnesses that were recorded in each state. There were 54 states, by the way, that was considered in the data set we are using. The 54 states included all the 50 states in the United States of America and 3 other communities of interest, and the last was multi-state, which represents the illnesses that were recorded in between states, sometimes en route somewhere or from a state. That is what multi-states represent. So over here you realize that California recorded the highest number of illness over the time period between 1998 and 2015. This will be seen clearly in the next slide. So what I did was I extracted this data to be able to get the top 5 states with the highest recorded illnesses between the time frame of 1998 to 2015. So that is what is shown inside this pie chart. So in this pie chart we see that California topped the charts, coming up with the highest number of illnesses, followed by Illinois, multi-state, Florida, and Ohio. I did the same extraction method to be able to see the trends in the years as well. So we realized that in 2004, that's when the highest number of foodborne diseases were recorded, followed by 2006, 1998, 2000, and 2001. So this gives us an idea of what really went on between 1998 and 2015, talking about how many illnesses or how many outbreaks was recorded or reported in each of the states and each of the years. Now, knowing the states with the highest number of illnesses, that's the top 5, we also studied the trends in the progression of the number of illnesses over the time period, that's the 18-year time frame. But we realized that when we take the highest, that's California, it started quite low. And then in 2006, there was quite a spike in the number of illnesses that were recorded. This could be attributed to a different, so many different number of reasons. It could be an increment in the population. It could be some form of infection in the local food stores around. It could be anything. And we realized that, funnily enough, multi-states started low and rather appreciated by the year 2015. So all this gives us an idea of how the states, how well they were able to manage the outbreak situations that they were involved in. From there, I went on straight to the main analysis, starting with the regression. So I ran a multiple linear regression using Python, and this is a summary of the statistical parameters that I looked at. So we have R squared, adjusted R squared, F statistic, omnibus, skew, kurtosis, and what have you. Actually, the most important part of the linear regression is the regression coefficient, but because of the number of data points that we are dealing with, we cannot project that on a simple slide. And so the main report is going to have that at the end, where the codes and their output runs were given. So let's go through these step by step. Talking about the R squared, this actually represents the proportion or the parts of the variance in the dependent variable. Over here, our dependent variable was the number of illnesses that were recorded. So if we are talking about R squared, then we are talking about how much of a relationship can be seen or drawn between our independent variable, that is the state, the location, the type of food, what have you, and then the dependent variable, that is the number of illnesses. So what we are really looking out for is there really a force from our independent variable towards our dependent variable? Is there really a dependence on the independent variable. But looking at the value that we got, that was 0.239, we can say confidently that there isn't much of a relationship between the independent variable and the dependent variable. The adjusted R squared is just to adjust for the number of independent variables that we are looking at. The F statistic actually represents a null hypothesis. So in the beginning, we just assume that all the regression coefficients have a value of 0. So whatever F statistic we get over here is going to determine whether there's actually any of the coefficients of regression that are significantly different from 0. So looking at a value of 14.19 for our F statistic, we can say that, okay, there are some values that are significantly greater than 0. Moving to the omnibus actually gives us an idea of the normality of our residuals. So having such a huge omnibus tells us that our residuals are not normally distributed. The Durbin-Watson tells us about the autocorrection. The Durbin-Watson is usually a value between 0 and 4. And if the Durbin-Watson obtained is 2, it shows that there is no autocorrection whatsoever. We recorded a Durbin-Watson of 1.992, which is approximately 2. So we can say that there was no form of autocorrection in our residuals or in our data. The Jack-Bearer is also another means of predicting the normality within our residuals. And this number, which is a very huge number for Jack-Bearer, also shows or juxtaposes what we saw earlier over here, that the residuals are not normally distributed. The skew shows the symmetric nature of our data. So if the skew is around 3, then we can say that, okay, if the skew is 0, then we can say that the data is symmetric. But having such a positive skew only shows that our data is skewed to the right or positively skewed. The kurtosis talks about the tailedness or the ends of our curve. Looking at a normality or a normal distribution plot, we see the bell shape with the ends sometimes flat or heavy. But this number of kurtosis, this huge kurtosis, shows that our tails are very heavy. And the condition number also shows the correlation between the independent variables. This condition number is just too high, which shows that the independent variables have a very high correlation between them. This makes it difficult to be able to determine the independent correlation between the independent variables and the dependent variable, because they have a correlation between themselves. You can't really tell what is happening between they and then the dependent variable. So this is like a summary of what we have from our plot. The most important part of the plot, the regression, is the regression coefficient, which shows the dependence, that it estimates the dependence or independence of the dependent variable on the independent variable. So a positive coefficient will indicate that when the independent variable is increasing, the dependent will also increase. And a negative coefficient of regression will show that when the independent variable is increasing, the dependent variable will decrease. We also have the standard error, which is just the errors of the estimated coefficient, and then the t statistic, which usually shows the ratio of the coefficient estimate to the standard error. We also have the p-value, which just shows whether our model is statistically significant. And then we have the 95% confidence interval, which also shows the whether the regression or the model we did was statistically significant. Moving on to the next method, that is K-clustering that we used, we got 3 clusters based on the number of the number of illnesses that were recorded. So this is our first cluster on the left, this is our second cluster on the right, and then we have our third cluster. Over here, we tried to do a cluster that was in a scatter plot. So we have little dots everywhere, maybe little dot of blue here, little dot of red here, little dot of green here, showing that we have one cluster here, one cluster there, one cluster here. But because of the nature of our data sets, specifically because our data set is really huge, we cannot have all those little dots going on here. It was a bit clumsy when I tried actually, so I changed some of the parameters of the code to be able to get a more cleaner look like this. So this is what our cluster looked like in a scatter plot. The next thing I'm going to talk about is how we made, or how I made, the methods I chose, that is regression and clustering, better. Now we know that the multiple regression I ran was based on linear regression, and linear regression is not so efficient for this kind of data set, because I am dealing with a data set that has a count variable in it. So to change or to make the results better, I can, instead of the linear regression inside the multiple regression, I can use a Poisson regression, a Poisson or a binomial regression to make the which is better suited for the data set, to make it run more efficiently and have better results. Now, looking at the clustering, like I mentioned earlier, because of the large data sets that I am looking at, there was a bit of a mess when I plotted the dots or the scatter kind of plots. So to make that look cleaner like it is looking now, I had to use the principal component analysis to reduce the dimensionality of the data sets that I am working with. So that is what I did to access. So we see here the second principal component, the first principal component. So the principal component analysis is what helps to give such a cleaner look. That's what helps this clean looking clustering. From there, now we have done our analysis, we have seen the trends in our data and what have you. We have seen how our states recorded illnesses over the years and all of that. I also asked myself how possible it is to be able to predict what happened after 2015 based on the data I have on before 2015. So we see the years marked by different color schemes. So you see the deepest color represents the nearest year, the lightest color represents the farthest year, and obviously the cases were much higher in the farthest year or in the older years than in the current years. We expect that because more detection methods and more mechanisms have been put in place, the situation should get better now. So that is what we see here. And over here, one interesting thing we notice is the data over here is actually a normal plot, unlike the one we saw in the original data set, which was not normal. It wasn't a normal distribution, but this is kind of a normal distribution. The essence of this part of the work was that if we can be able to make predictions based on the data we have on past outbreaks, then we can go on the action side and not on the reaction side. Because in the first place, the fact that we are reacting to what has happened, that is the fact that we jump in after the outbreaks occur, is what is causing us to lose that much money in hospital bills and what have you, and we lose that many lives. But then if we are able to predict that, let's say in the year 2024 or 2025, there is going to be about 5,000 cases and about 1,000 of them are going to be recorded in Washington DC, then we can make positive decisions, or we can make decisions that will actually prevent that from happening based on the campaigns or the adverts that we run on food safety, something as simple as washing of hands and all of that, those kind of simple hygienic rules. And we can also increase how much safety runs we make in our food industries, how much safety rules we make, safety laws, even legislation that we put in place. Interestingly enough, it can also help the kind of census that we even produce, because if we know that, okay, we can predict that in Tennessee in the year 2024 there is going to be this many diseases, but Tennessee doesn't have a particular reagent that is used in the normal biosensors that we have now, then we can tweak the biosensor in a manner where Tennessee residents or the food companies in Tennessee or laboratories in Tennessee can use the biosensor with the reagents that are available in Tennessee. So if we look at it critically, we can see that being able to predict what happens in the future is what is going to actually bring the numbers down to the point where we are expecting. Because if we can predict, then we can prevent it from happening at all. There will not be the chaos or the outbreaks that leads to the deaths and the loss of money and resources and what have you. Concluding, we realized over the analysis that the state and the year with the highest reported number of illnesses was California in 2004 respectively. So California recorded the highest number of reported cases over the time period between 1998 and 2015. And among the years, 2004 had the highest recorded cases. Now, just as initially speculated before the analysis even began in the first place, people thought that because we have switched from the traditional home-cooked food to eating out and getting fast foods and quick-to-go meals, that is what is causing the high numbers of foodborne diseases, even though we have better technologies to detect now. The analysis proved that right, because among all the illnesses that were recorded, those recorded from restaurants had the highest number. So people who got sick the most were people who ate from restaurants. And norovirus was the pathogen that caused the highest number of infections. Meanwhile, Listeria monocytogenes was the bacteria that caused the highest number of fatalities. It means the highest number of people who died from Listeria monocytogenes, which is a very stubborn bacteria, by the way. When we look at the summary table that we obtained from our multiple linear regression, we realize that the analysis was statistically insignificant. However, it opens us up to the possibility of using data analytics with the help of computer programs like Python and R to be able to analyze the trends in this kind of data and how important it is to real life applications. The CDC, WHO, Food and Drugs Authority, Standards Authority, they can take these outcomes in the data analysis, and then they can make actual decisions that will affect human lives. We can also say that further research is definitely recommended to explore specific factors contributing to the dynamics of this problem, because this analysis is not enough to delve into those dynamics, and then we can develop the right models needed to predict and prevent the impact of foodborne disease outbreaks on public health. And this is going to go a very long way to save lives and to save resources, money, most importantly, because the people who suffer from this the most are those with less money. So if we can save that, then we can help impact people's lives. These are some of the references that I used in the work or in this project that I just went through. Thank you very much. Thank you for the attention and for listening.